remind you of a few points here with an eye towards the commissioning work that we're doing. calibration within the station is actually very good quality now, and is giving us sensitivity and beam shapes, digital beam shapes, which are very well aligned with what we expected. So the image on the bottom right here is showing some measured beam widths approximated. We can use the single stations to observe pulsars. This was mentioned earlier as well. We've now detected 50 known pulsars with single stations, and also have had some initial encouraging signs around the polarization properties of the pulsars as well. We're now starting to test tide array performance, that is combining the stations together to observe pulsars. That's looking good so far, but we don't have yet for real-time calibrations that will give us the full tide array coherence. That's coming soon, and then we'll be able to have higher sensitivity observations. The plot on the right here is just showing a bunch of MWA detected pulsars, and what you can see in that diagram, the red ones that we've detected with SKA low are the ones that are brighter. We're finding the brighter pulsars of the ones that we should be finding, basically. There's a couple of plots here that show initial results from the tide array testing. Here too, we're detecting a bunch of pulsars. So these are just pulsar observations as a function of time on the horizontal axis and frequency on the vertical axis. Full bandwidth, 75 megahertz bandwidth observations showing expected properties of known pulsars. And we're now able to get the system down to microsecond time resolution. Okay, even quicker. So we're also testing the array performance for imaging. Showing that the delays within the system are all as expected. We've detected phase closure, which means that we can calibrate the array and measure the sensitivity, as I mentioned. This is using signal to noise ratio of visibilities on bright compact calibrators. And apart from some deviations at the lowest frequencies, which I'll explain in a second, the measured data are really well aligned with what we were expecting. Again, indicating that the station calibration is really being done well. The discrepancy at the lowest frequency, we think, is because the SKA models that we're using for the calibrator observation, for the calibration of the calibrators, the SKA model is not as good as it should be. Beam size is bigger. We haven't taken into account the field sources. We think that that's the cause of the extra scatter down here, but we'll fix that up soon. Okay, now I'm going to skip over this very quickly. These are visibility data for a single baseline here that were collected on the way to producing the first image that you saw earlier. The exact behavior of the data, the raw data here, which by the way, not even flagged for RFI. There's two aspects here. One is the overall envelope of response. That's due to the antenna response pattern, which we can remove on the basis of the electromagnetic simulations that David talked about earlier. And also the mixing of the polarization state. That's because of the relative rotation of the stations. But we can correct both of those effects and wind up with corrected visibilities, which are nice, flat, stable, and apparently unpolarized, which puts us in good state for calibration using a field model, which also behaves very well. These are amplitudes and phases on a single baseline after having done some self-calibration, which by the way is a really delicate affair with only 4 stations, but if you're careful, you can do a reasonably good job given the instantaneous bandwidth of the system. And the residual wiggles here are because of field sources in the field of the calibrator. So here's the first image, as you've already seen today. So looking very good, that has 85 sources in the field. And when we compared the measured flux densities to ones known from the Murchison wide field array, they gave us, again, a very good indication that the apparent sensitivity pattern of the telescope is consistent with the expected station beam size, even though we didn't give the calibration any indication of what the brightness of the sources should be a priori. So self-calibration process is stable enough to give us expected flux densities, and the stations are well calibrated. Okay, so now we're finalizing our first version of a calibrator database. We're doing that on the basis of observations being carried out by the science operations team. And we're going through a whole range of tests to first figure out which calibrators, and in particular, not just the calibrator themselves, but also the field sources, which of those pointing directions are suitable for calibrating the telescope, and also testing the calibration of the telescope as well. So it's a bit of a multifaceted process as we work through figuring out which calibrators are best for us and making sure that the calibration scheme is solved. Last point I'll mention is that we're starting to test the pipeline which will be used as the actual calibration system for the telescope. And through that process, we've been able to find produce the first full bandwidth bandpass plots from the telescope as well. And everything is looking really good at this point. I won't go through the details due to the time, but everything is looking very good, even though we can only observe several tens of megahertz simultaneously at this point. We can stitch them together and it all looks consistent. Right, so recap here. These are the main takeaways I'd like for you to take away from the science commissioning effort so far. We can demonstrate clearly that single stations can be well calibrated and that they can point and track correctly. Tide array results are looking very good with the real-time calibration loop coming up very soon. We can calibrate and image the array with about arc-minute resolution. And we're finalizing the list of calibrator sources as well as testing the calibrator pipeline at this point. Right, so last slide is what we're doing next. Well, we've done about 80% of the A0.5 commissioning tests, with the remainder carrying over to the 16-station array that's coming very soon. We're finalizing the plans for that 16-station array, and we'll then be pretty much right away making the plans for the 68-station array, which is going to be hot on the heels of AA1. Finalizing the revised version of the calibration plan, as well as a plan for beginning work on plans for a commissioning survey or a sequence of commissioning surveys. And through all of that, working very closely with these adjacent teams. So AA1, the 16-station array, will bring us a number of different improvements. First and foremost is increased number of stations is going to help us so much to be able to calibrate the array much more confidently and give us a lot better handle on the overall system performance and stability. So with that, I'll take any questions. Thank you.
Can you come up and use the microphone?
Purely on the basis of the station calibration errors that we can quantify, we think we're losing only about 1 or 2% of the sensitivity of the station from an internal lack of coherence in the station, basically. The station beam shape, frankly, is a little bit harder to not to be too quantitative about at this point. We're in the middle, basically, of developing proper predictions for what the station beam shape should be in those sort of drift scans that I showed you, to be able to do a proper comparison. At this point, that's more qualitative than the sensitivity loss estimates that we've made. If that makes sense. Yeah.
So with the calibrations, do you have to constantly change the calibrations based upon something like equipmental environmental conditions, such as like it's a really cold night or a really hot day? Do you have to recalibrate? How have you been accounting for that?
Yes, that's a good question. So there's definitely thermal effects within the station. But for the coherence of the station itself, what matters is the relative changes within the station. So if all of the cable lengths are getting longer and shorter together, then there's no internal calibration correction. So the number I was referring to before is the sort of 1 or 2% maximum coherence loss that is from the thermal variations, basically.
If when they fully complete the entire SKA, because of its size, would you still have to then now calibrate the different temperatures at different regions because these might not expand, these cable expansions might not be the same?
Yeah, so I think, sorry if I interrupted you.
No.
Okay, so, well, to be fair, we're still finalizing what we think the real station calibration plan is going to be. What we've demonstrated is that we understand which times of the day, quote unquote, both solar day and galactic day, when we can do really good calibrations. We expect to do the delay calibration part probably pretty frequently, and that will, deal with some of the thermal effects. Pretty infrequently actually. I know there's like an overall gain calibration to be done within the station, and that's probably done more frequently, maybe once or twice a day. But we're still pinning down details on the exact strategy for when and how we do that calibration.
Last question.
Okay, so I'm looking at the solution for the bandpass calibration.
Okay.
And around 250. Yes. So I'm thinking, is that the response from the system, or there's something else going on?
No, there's quite a broad band of RFI there. Actually, I forgot to mention that. Thanks for raising it. So there's a pretty good chunk of 20 megahertz width, maybe something like that, which is full of satellite RFI. So in fact, that section of the spectrum could well have been blanked at this point. We just left it alone for the purpose of display here. There's a couple of spots in the spectrum where satellite RFI occurs around 130 megahertz, off and on. And that chunk that you mentioned is always full of satellite RFI. So that's why it looks crazy.
Thanks very much. Next speaker is Lewis Ball. Is going to take us into SKA mid-commissioning.
Not so much commissioning this time. We're running a little bit slower with SKA mid and SKA low. And so, excuse me. So this is very much a presentation on the progress of construction for SKA mid. I just want to point out, I'm the Director of Operations. I'm giving a presentation on behalf of programs, so construction, so bear with me. And it will be a gallop through the complicated construction activities. The authors of this presentation are on the last slide. So lead author is Ben Lewis, speaker is Lewis Ball. There's no particular coincidence there. So SKA mid in South Africa is the mid-frequency array for SKA. It will operate between 350 megahertz and 15.4 gigahertz. So it's AA star that we're building at the moment. So this is array assembly star. That's the current goal of the construction program. It will comprise 144 dishes, both the 15-meter SKA design dishes and the 64 existing 13.5-meter meerkat dishes, which will be incorporated into the array. In terms of overall numbers, what we've currently got to is that 16 of the dishes have been manufactured. We're roughly 4 years into a 10-year construction program. Something like 34% of the program has been completed in terms of the earned value. There are 7 of the dishes that are currently on site and in various stages of being assembled, and the civil infrastructure is about 70% complete. And it's a very significant part of construction projects like this that are infrastructure as opposed to the more high-tech elements. In terms of the SKA mid science milestones, we're still in the early construction stage. The very, very early first beginning of commissioning activities, currently ramping up now. Science verification for SKA mid is expected to start in mid-2029 and to continue then until the start of true science operations which is currently anticipated in 2032. So quite a long timeline and roughly 2 years behind the equivalent milestones for SKA low. In terms of the construction milestones, which are different from the scientific milestones, you can see on this slide both SKA low above the line and SKA mid below the line, again demonstrating this roughly 2-year difference between SKA low and SKA mid. But emphasising that these are the construction milestones, and the science milestones lag the construction milestones considerably. So much more relevant to look at the science milestones in terms of external community, what your expectations may be about SKA deliverables. In terms of who is involved and the countries involved in SKA mid construction activities, there's Australia, Canada, China, Germany, Italy, South Africa, Spain, Sweden, Switzerland, and the UK, all directly involved in SKA mid through a range of institutions and organisations shown on this slide through their logos. And in particular, I want to identify the South African Radio Astronomy Observatory, which plays a very significant role in both construction and ultimately in the operations of the observatory. And in terms of building the SKA software suite that will operate the observatory, again, a very international activity involving Australia, China, France, India, Italy, the Netherlands, Portugal, South Africa, Switzerland, and the UK. And there are resources coming in from more than 30 suppliers from those 10 countries and some 160 named key personnel who are part of that, that global effort to develop SKA software. Local engagement and participation is particularly significant for SKA mid. We draw staff and contractors in particular from 4 local towns which are in the region where SKA mid is being built. And there are 275 locally employed people through the prime contractors, Paradenko and SETSI 54. Of those locally employed people, 54 are female and 172 are identified as youth in the South African vernacular, which identifies youth employees as being between 18 and 35 years old. And there are some 14 local small, medium, micro enterprises from those 4 towns that are involved in delivering the infrastructure work packages in particular, employing a further 38 members of the local community. So very significant, and we have a structured procurement process for those activities that take place in the local region that first looks at opportunities to employ people and contractors from those 4 local towns, and only after that, if necessary, do we broaden the scope of procurement. SKA mid builds on the very significant success of South Africa in delivering the Meerkat telescope. Meerkat's built and operated by South Africa through the South African Radio Astronomy Observatory. It comprises 64 13.5 metre dishes. It's the largest radio telescope in the Southern Hemisphere today. And it's an SKA precursor telescope. And it will be completely integrated into SKA mid. And the Meerkat extension project, which is currently underway, which is funded by Max Planck Gesellschaft in Germany, by ENAF in Italy, and by Soraya itself, will add 14 of the 15-metre SKA dishes into Meerkat, and that then will be incorporated into SKA mid. And so, as I said, Soraya contributes in multiple ways into both the construction and operation of SKA mid, delivering some key construction contracts and employing the majority of the staff for SKA mid in South Africa. Where are we up to? So 4 dish pedestals are complete. 3 of the dish reflectors have been lifted onto and installed on those pedestals. There are 3 further dish structures on the site, and all other major dish subsystems are available for SKA mid AA 0.5. In terms of the feeds, the band 1 pre-production units are under construction. Band 2, the construction of the feeds is well advanced, and the contracts have been awarded for band 5, and all of the dish feed controller systems have been completed. And infrastructure work, which is the first phase of construction, is actually approaching completion. So the digital mobile radio system is complete and in place. Some 70% of roads and access tracks have been completed. 85% of the foundations for the telescopes have been built, and 70% of the underground and 25% of the overhead fibre has been completed. And a fully operational integration and test facility with a 4-receptor system running SKA software is in place in Cape Town. There are very significant challenges in delivering SKA mid in terms of the collaboration and governance aspects, including in terms of technical risk and design maturity. The SKA Engineering and Advisory Committee has started to refer to the process of conducting the crescendo as we try to scale up everything towards the full scale of AA star, a very significant challenge. And cost control has proven to be extremely difficult for SKAO, not least because of the process of starting this incredibly complex project as the world went into a global pandemic and closing of borders and disruption of international supply chains. RFI, radio frequency interference, is a very specific challenge, particularly for SKA mid, where we're constructing within a world-class operating radio telescope that continues to do science. So Meerkat is continuing its scientific operations while we're building SKA mid. And that requires some very careful cooperation and collaboration. And in particular, we've very recently had to source 3 old cranes to undertake the heavy construction activities, particularly in the core of SKA mid, in amongst the Meerkat antennas. Self-generated RFI is a very big issue for both SKA telescopes, and the thresholds for radio frequency emission from our own systems are many orders of magnitude stricter than military and astronomy standards. And so that requires lots of additional development of the electronic systems for SKA mid and for SKA low. And very specific facilities have had to be set up and calibrated in order to stay below these limits. You get some sense of the RFI challenges from a couple of plots here. The one at the top right shows commercial and military EMC standards, and the green lines, and the red and blue lines show the thresholds, the maximum thresholds for RFI or EMC emissions from SKA systems, many orders of magnitude below those for other purposes. And bottom left shows the typical radio frequency emission from modern cranes, which you can see at the top of the plot there. Again, many orders of magnitude above the thresholds that we're required to operate in. So a tremendous amount of work going on to manage those activities. And this plot shows the fact that, as I've said, we're building SKA mid in amongst the antennas that make up Meerkat, and managing the balance between continuing the scientific program, which is enormously successful, of the Meerkat telescope, while at the same time building out SKA mid. And SKA mid completion represents the future of Meerkat science. And so we're trying to balance those two. Is a very, very complicated process. From a construction point of view, it would be much more straightforward to stop doing Meerkat science, but that's not the best approach for the scientific productivity. So I'll skip over the ITF test results, but fully operational ITF in place in Cape Town. More detail on infrastructure progress in the roads. Some 84% complete in terms of the wearing roads, 180 kilometres of new roads required, and some 520 water course crossings. So a tremendous amount of activity there. Just to highlight a couple of details here in terms of building foundations for telescopes. Some 8,500 cubic metres of concrete have already been put in place for antenna foundations. And they're making very good progress in completing those foundations, which are essential, obviously, for installation of antennas. Roughly 1,600 wooden poles have already been planted to carry power and fibre reticulation across the site, and nearly 190 steel power poles have been put in place. Only 30 of those remaining, and stringing of the power and fibre cables should be starting essentially around about now. We're building a remote power station for one of the antennas in AA Star, and ultimately 21 of the most remote, well, the 21 most remote dishes for the baseline design will be powered by individual standalone power stations. The current minimum viable product, which is already passed its factory acceptance testing, is informing the design of those remote power stations, but also the design of the central power stations that have to be built and operated in order to be able to operate both SKA mid and SKA low in Australia. So we're learning from this process what's required for SKA low as well. The mid correlator beamformer correlator has already been installed for AA 0.5 at the telescope site. The final correlator for SKA mid will use a newer COX architecture, and that'll be installed in Cape Town. That's passed its final design review and it's under development. Dish progress, I'm going to skip very quickly through these. So handover of first dish on the 4th of May 2025. Testing very much underway and will continue through to the end of the year. In terms of dish design, there was a lot of work to ensure that the dishes actually meet specifications, and in particular the stability of pointing was quite a big issue that resulted in substantial changes to the design, and some 30% more steel was required in order to get the required performance. 7 dishes are in various stages of assembly on the site, and you get some sense of that from the images on these next couple of slides. So 2 antennas, backup structure currently being assembled, ready to be lifted into place. Feed indexes, 4 units already delivered for AA 0.5 are complete. Sub-reflectors being built by 2 different contractors, 16 being built in China, 44 being built in Spain. The sub-reflectors for AA 0.5 are delivered and ready for installation, one of which of course is already in operation. Key achievements in terms of feeds. Band 1, essentially final design and test readiness is completed. Pre-production units are under construction. Band 2, construction is advanced. Band 5, contracts awarded, so some way away. Many of the cryo systems have already been accepted and dish controller systems completed. Just one thing about Band 5, there's lots of technical detail on these slides, but I'll simply gallop over these. The Band 1 feeds are very large, 1.5 metres tall. The quad-bridge feed horn design and technical details that I don't have time to go through. Specific qualification and production test facilities in place for Band 1. Band 2, very different style of package, and Band 5 comprises 2 different systems within one integrated feed package. Cryogenics, 70 cold headers already delivered, 4 compressors on site. SKA mid is starting to come alive with the first antenna collecting signals. and in particular now with a spectrum on Sky showing neutral hydrogen detection. Very exciting, just achieved in the last couple of weeks. System temperature from the very first tests showing 16.7 Kelvin against a design specification of 15 Kelvin. So remarkably good result, essentially as we turn on the system. And finally, we can actually see the features within our own galaxy by observing in drift scan mode past this very first antenna, even before we have the ability to track the sky. And you can see the comparison with a reference observation. So what's the outlook? What does it look like? Infrastructure program should be completed next year. We will be delivering more than 2 dishes per month between 2026 and 2028, which is enormously challenging. AA 0.5 should be completed during 2026. The final central beamformer installation is due Q4 2026, and AA2, the stage where we will start to deliver science verification data to the community, is scheduled for 2029. So thanks very much for your time. Quick gallop through construction progress. Lots more information available at the link listed here, and also names of the authors responsible for the presentation. Thank you.
Thanks, Lord. We can take one quick question while Anna gets started.
Smartphone connected.
You might put the yellow and I'll repeat it.
That's great. You want me to walk somewhere?
I'll repeat it.
Oh, yeah, good. What's an estimate how much faster construction would happen if you ignored Meerkat or turned it off? No. There's not a lot of point because it doesn't make sense for us to do that.
Okay.
It doesn't work for South Africa, for the science community. And as I say, so radio in South Africa is an integral part of the project. What we're trying to do is constantly optimise the approach in order to deliver the best for the community as well as for the observer.
Thanks, Elizabeth. And our next paper is Anna Jenkins on use of closure quantities within a single SKA station transmitter fault. Thanks, Anna.
Hi, my name is Anna Jenkins. I work for CSIR on SKA, part of the team responsible for operational support and integration, test and birth. A big part of this is making sure that SKA load works and produces the data we expect it to, and then to make sure it stays in this state. So I'm going to be talking about the use of closure quantities for antenna signal chain fault detection, SKA load. So first, I'd like to recognise and acknowledge the traditional owners of the lands on which the facilities are located, pay my respects to elders past and present. Australia's Indigenous people, the first scientists, and long-standing knowledge of the universe, and continue to build today. I acknowledge the Wadjuri Yamaji as the traditional owners, native title holders of the Yari Environment Elder Gundera, CSIRO, which is the Astronomy Observatory, where we are building the SKA telescope in Australia. We've also acknowledged the Waichak Noongar as the traditional owners of land where our Science Operations Centre is situated in Perth, and the Southern Yamaji, the traditional owners of the land where our engineering centre is situated. I'd also like to acknowledge the traditional owners of the land we're living on today, Gadigal people of the Eora Nation, and our respects to their elders past, present, and recognise their continuing connection and to culture and their custodianship of the land, seas and water. And I also pay my respects to all the First Nations people in attendance today. So first, a bit of background. You've probably heard this several times now. SKA low is a low-frequency interferometric radio telescope. It's being built in the radio quiet zone in remote Western Australia. It will consist of 300 aperture array stations distributed up to 40 kilometres apart. Each station is comprised of 256 dipole antennas receiving dual linear polarization. As of last week, more than 9,000 of these antennas have been deployed. Also naturally due to the remote location and distributed nature of SKA load, finding antenna faults and installation issues with incompetence is very important. So this is just a picture of one of the clusters under construction. This cluster is going to consist of 6 stations, and each of these 6 stations is going to have 256 antennas. Yeah. So what's involved in this closure quantity testing that we do? So the first step is to capture single station visibilities. So what we do is we treat each antenna within a station as a telescope, use the station as an interpreter. So this is purely a station level test that's run on each station separately and individually. So we capture a snapshot of the full sky signal antennas because the antennas actually receive signal. And this signal is then channelized into coarse frequency channels by the signal chain. And this channelized signal from each antenna is correlated with all of the signals from the other antennas to form correlated visibilities for every baseline, and then this is saved to disk. So this is an example of the signal received by a single station at an instant. So this is a full sky interferometric image generated based on correlated visibilities taken from a single station. So we get the signal from the full visible sky, so everything above the horizon. Yeah. And so these full sky visibility data sets are captured as part of the station calibration process, which means that the closure tests that we run typically don't require capturing more data, instead we're able to just reuse data that was already captured. Although it is worth noting the station calibration process requires visibilities across a range of frequencies, whereas these closure tests use visibilities from just one coarse frequency channel. So you can see the full sky here with the galaxy on the right. So closure phase. Closure phase was introduced by R.C. Jensen in 1958 as a way to compensate for the poor phase stability present in early very long baseline interferometry. So closure phase is the sum of phases of complex visibilities for baselines or in the triangle telescopes. So in our case, our telescopes are the individual antennas. Individual telescope phase errors, such as interference due to the ionosphere or troposphere, or phase error due to uncompensated signal chain delays, cancel out in the calculation of closure phases. The term calibration insensitive is sometimes used, and what this means is that the closure phase of when you calculate on uncalibrated visibilities is the exact same as if you calculated on those same visibilities after calibration. So you get a quantity that's based on the true phase terms with no error term. You're not recovering the absolute phases, you're just getting a relative phase term. And similarly, we have closure amplitude, which operates on amplitudes instead of phases. This was introduced by Twist et al. In 1960 as a way of studying brightness distributions of radio sources. So closure amplitude is calculated as the ratio of visibility amplitudes, so that the complex gain errors in the amplitude terms cancel. The numerator is the two disconnected baselines, and the denominator is the two baselines needed to complete the quadrilateral. This gives us 3 ways of calculating it, two inverses, with 2 of these non-redundant. So from each 2 of these, you could determine the third. We also often use the log of the closure amplitude or the log closure amplitude, since this is easier to work with both ways. And this changes this closure amplitude fraction into a set of additions and subtractions, obviously. So how do we actually use this in our test? So what we do is we take the correlated visibility of a single station. We don't need to do any calibration on it. We can then calculate the closure phase for every possible triangle of baselines and the closure amplitude for every possible quadrilateral of baselines. So as I said, there are 3 ways of calculating closure amplitude. In our case, we just choose one of them. And so we're just taking a subset of possible ones. So if the sun is reasonably high in the sky, dominates the visibility, and is essentially resolved, so it acts as a point source. The closure phase and low closure amplitude of an ideal point source are both 0. So as part of the test, we do a sum of the squares of every closure quantity that contains a particular antenna, compare it to the sum of the squares of the closure quantities of the other antennas. And so faulty antennas show up as outliers, which we can pick up through various statistical methods. So here's just a bit of justification that this will work. So this was histogram closure phases from a daytime observation, showing some pretty dense clustering around 0 radians. That's on the left. And on the right, we have the same for low closure amplitude with some very dense clustering around 0. So this next slide is an example of the summed squares of closure phase, the same data source, except we've separated it out by antenna number. So along the horizontal, we have the antenna number, which has been grouped into color, like 16 colors, just for other signal chain reasons, and makes it look a bit nicer and more readable. And then along the vertical, we have the sum of the squared closure phase. For every closure phase, it contains this antenna in the triangle you use to produce that closure phase. So the units here along the vertical aren't important, they're just like a relative measure. And so we get these two antennas that are very strong outliers that have a very high relative sum, which indicates that there's be some issue with the signal chain for those two antennas. And so what happens when we run the closure amplitude test on this, since it's this closure phase, we get this. So we get the exact same three outliers in a very similar looking plot. Likewise, when we run the station calibration process on this station at this time, we get the same outliers, serving as a really useful form of cross-validation between these three tests. But there is worth reiterating that the station calibration process requires a range of frequencies that are unspecified, whereas these closure tests only require one coarse channel of frequency and a set of calibrated visibilities. Yeah, so it does indicate that there is some issue within the signal chain for those two antennas. So naturally, the next question to ask is, what can we do when the sun doesn't dominate the signal? So what we do then is we use a diffuse global sun model to model the visible state on the station at the time of the observation. Optionally, we can also include a sun model here if the sun's going to be low relative power, although then you have to work out relative power. It makes things a bit more complicated, but there are techniques to do that. We have the high precision electromagnetic stimulated antenna beam models for computed embedded patterns and saved digits over a range of frequencies. This includes full polarization, mutual coupling of antennas. These were discussed in the talk earlier. Today, simulating the beam models. So we use these together. Like we use the diffuse global sun model with the beam models for total visibilities, corresponding to captured visibilities. And then we can calculate the closure phase rates, triangle, closure or quadrilateral in this model visibility. We can then take differences and compare them. So we can get a measure of the quality of an antenna by taking the sum of squared differences of the closure quantities that contain that antenna between the model and the observation. So we're not assuming here that the closure quantities are going to be close to 0. We assume that the model is going to produce good enough results that the differences between the two are going to tend towards 0 for antennas. It's also worth noting that in practice, we don't calculate every closure quantity. Instead, we take a subset of them, which bias longer baselines, since these provide more signals. And that's more important when there's no source time. But it's still unbiased in terms of per antenna. So this is just a bit of justification that this is going to work. On the left, we have a closure phase like density plot, a model versus the observation. And on the right, we have a plot of the local closure amplitude of the model versus the observation. And the black line is the axial y line. And so the closer to that line, the better the correspondence between the two of them. So we can see that they do look fairly nicely correlated together between the observation and the model. So that does indicate that this test will have merit and it is going to work. So back to the per antenna test. This is now a comparison of sum squared differences for antennas. Rather than expecting that like just the closure quantities will go to zero, difference goes to zero. So the test still works, but there's a bit more noise present. And we are still able to pick up these three clear outliers. And we think this like variation has to do with noise and imperfections in the SKA model. So this is a real example from actual data collected. These three outliers. One of the common failures we know to occur is what we call the polarization swap. So SKA low antennas receive signal in two polarizations, labeled X and Y. So a polarization swap is when the cables for the two polarizations are get the opposite slots. So you'd have the X cable going into the Y slot and vice versa. So that's just an installation issue. We can easily simulate this in the state data to be correlate between polarizations. So we simulate what will happen. We swap the cables by rearranging the visibility data and then rerunning the test. So we'll simulate a swap of these three outlier antennas, and if they were installed wrong, then the swap would return as what we expect them to be. So let's see what happens then. So we can see that two of the outliers are just damaged and returned for normal range within the antennas. So we can be quite confident those two antennas were outliers as a result of polarizations, like the engineering team know to investigate this. However, one of them wasn't fixed, so we can rule out a polarization swap for that antenna and look at other diagnostics to find towards what the fault may be. So yeah, this method is a very useful first step in finding faults in the antenna signal chains and erroneous connections prior to any station calibration. It's been implemented in SKA low as a short functional test. It's executed just following station construction and integration. There's currently more than 9,000 antennas, and there's going to be many more in total. And so the ongoing construction phase of SKA low, this method is proving to be key to finding and correcting antenna signal chain faults. And we've successfully found these faults.
Questions?
Cool talk, thank you. My question is how in a physical system that failure manifests if it's always one side of the phase circle. So if you have a whole bunch of triangles that have this one antenna and that antenna is faulty, in some of those phase closures that'll be plus some radians. Is it minus some radians in other? Because in your relative plot, I'm picturing, plus 100 minus 100 over many, many sums, and you end up with a 0.
Yeah. So that's what we do is we square them. So that way you always get an absolute value. That way the relative measures won't compound.
Yeah. So you probably did this for XX and YY separately, but if you have off-diagonal terms in your gains, then both the closure phases and closure amplitudes will not work. The cancellation will not happen as you showed. So have you considered a more general version of closure quantities like closure phases and things? So you can also diagnose the off-diagonal quality of your calculation.
No, rather I reduce this test into like just the XX and Y polarization. that could be a good thing to invest capital.
More questions? No, thanks again. No, and
I'm a champion on Taiwan from astronomical theory and the next session. So the first speaker is from Edgar Boyden from the side. So we're going to go up to 13 and okay. Next thing to find is for the question. Sure.
So when you hear the problem, it's really the problem. Again, we sort of talking about the SKA line. I'll get to it. SKA probably everyone knows. We're talking about the low frequency telescope following the beginning format. And thanks to delivery through our voice and acceptance testing of our client's verification.
You're just trying to say.
Okay, so as I said, we're talking about we're going to talk about how we verify the requirements. So we have 438 of these with the final telescope and our factory acceptance testing for AT. So the OCBF for all that playing this for the telescope, so don't worry about anything that's too much other than backstage instead of the program, the numbers get bigger. And specifically for AA1, we have the pulsar search beams, the major step change there. We did the FAT for AA0.5 in November 2023, and FAT for AA1 was last year. So the path towards passing our FAT started in last year in August, and we had a largely manual process using Jupyter notebooks, producing graphs and reports on the screen. We had some visitors from SKA to observe. And we got a conditional pass. We had to do some more work to fix some bugs and so on. Following that, there was a Delta FAT to address those differences, which was performed online this time in December last year. More automation, and we successfully demonstrated 269 out of our 530 requirements. Memory vendors and multiple telescopes without need to do them today. And we got a full pass this time. So some of the numbers that we did demonstrate, 256 in brackets there, stations, Our signal processing doesn't particularly care about the difference between a full station and a substation. It's just a label that's applied in software for signal processing. The process facility, I think that's bandwidth, both for correlation and for the pulsar switch and time endpoints. As for example, the signal to noise ratio is ideal, close to 3%. Time step accuracy 3 milliseconds for correlating, 3 microseconds for more sensitive pulsar switch and time endpoints. And so on. So how do we demonstrate these requirements? We have these things called Parenti test cases or PTCs. Our team is called the Parenti team, named after a large lizard. It's found in the desert after the telescope is being built. And we have 4 categories of these tests. Visual inspection is performed by humans, and we have interface, functional, and performance categories, which we can automate to varying degrees. Some examples listed on the slide. And specifically, the tests are described in a spreadsheet, pretty typical of a test specification, a series of steps to do, labels, tells you what to do, what you expect to see, and then on the right hand side, they have to the requirements that you have to deliver. So here we'll just have an example. Test case number 5 is about data ordering and correlation outputs. So to implement this stuff, there's the main steps that we do. So we set up the infrastructure, network routing, we configure our software components, our subarray talks to our signal processing. We have a thing called the scenic, which stands for the configurable network interface card. It's going to be another talk about that on Wednesday. And we can configure all our software. We should be scanning for the subarray, which depends on observation. Attach the data to a PCAP file, analyze that, produce some reports, and then ultimately give a file stuff out, hopefully. So, in terms of actually running this on hardware, this is kind of what it looks like. The big box on the left represents one of our FPGA host servers. The less big box on the right is the network switch. It needs host various software components that are deployed through Kubernetes. So we have software to control our scenic, which is assigned to a particular FPGA card. Likewise with our processor. The connector runs the network routing on the switch. The test runner at bottom left tells everything what to do. Software is actually more complicated than this. So the test runner talks to the subarray. There's another hop in between the subarray and the processor. But the gist of it is that the test runner says, hey, subarray, do this. And the message gets through to the processor. The data flow of a test is like this. The scenic produces the stimulus files, the stimulus signal that goes into the system under test when the FPGA controlled by the processor. Those network packets are routed through the connector. The output then goes back the same way into the scenic, which can write to the hard drive of the test server, and we can do our analysis in Python to make sure that everything is as expected. So that's the full picture there of control flow and data flow during our tests. So the main 2 automation tools we use are PyTest and GitLab. PyTest describes itself as a framework that makes it easy to write small, readable tests that can scale up to complex scenarios. And some key features of PyTest that we use are fixtures, parameterization, and marks, just select 4 categories of test. So we can have a look at how this looks in practice. There are some example PTC number 5. So we have 6, 18, 64, 256 stations. This test is repeated for. And we have some fixtures to provide our software components that we communicate. In PyTest, the ultimate pass or fail of the test is decided by assertions, which can be just a plain Python assert, or here we use NumPy to help us check that all the elements of our array are close to each other. And this is the typical output of PyTest. Headers look for clarity, but you can see here that we've selected to run PTC number 5 and 4 different iterations of the test. The other thing we make a lot of use of is GitLab, which they describe themselves as helping you to deliver better software faster. I should make clear that this is their words, not mine. This is meaning that SKA told us to use GitLab. I've got some features that we do use. There are CRI and CD pipelines triggers, which are the way that one software project or one firmware project can run tests in another project to run. So when we change the firmware, we could regression test and the software still works. And we have schedules. So we have some very long duration tests that you don't want to run every time you make a change. So we can run them monthly. This is a typical view of a, well, this is perhaps a slightly optimistic, typical view of a GitLab pipelines. It's green. If you click on one of these pipelines, you can zoom into the jobs. I should mention also that we inherit a lot of these from common SKA software. We didn't run this ourselves. All of our stuff runs in one of the top Python KX test. So the green ticks are nice for peace of mind, but they probably don't convince the customer that everything works. So we also produce some reports, graphs and numbers and so on. PTC5 chose because it produces nice colors. And we have here the 256 station example, where we use obviously a contrived input sequence that gives a gradient in the gain across the stations, and it's kind of a stepped sawtooth sort of pattern with phase. So this gives us quite good confidence that the data packets are coming out in the order that we think they would. That was not the case, so it's very likely that our test will be able to detect the items which were trained. So along this process, what have we learned? From a project management point of view, it's important to prioritize the tests in terms of test the most important things first, so you don't get bogged down in trivialities. And your test should mimic a typical use case of the telescope. It's also good to agree in advance on the test protocols rather than doing experiments on the go. From a software engineering point of view, reliable test tools are very important. So this includes the infrastructure, both hardware and software, as well as the test code itself. It's very difficult to diagnose whether a bug from a high-level test. These tests can tell us that something's broken. What do you change to make it work again? It's very tricky. So we try to help that by logging all kinds of stuff that our engineers can use. And ultimately, a test that you don't run, that you ignore the output of, isn't going to tell you anything. So it's important to actually execute your tests often so that you know when things break. The sooner you find out it's broken, it's kind of helps you figure out what might have broken on the last few. So the future for low CPF is our AA2 delivery, and the numbers will get bigger. It's not super exciting. You just add more hardware largely. But the new step change is the zoom correlations. So that's a new feature. And if you're interested in more about how low CPF actually does its business, there's another talk on Wednesday morning. Yeah, so probably didn't mention that the signal process. I didn't mention the signal process is doing FPGAs, but I didn't mention that the network routing is also custom software running on network switches. So it's more details on Wednesday.
Questions or comments?
Hi, Andrew. Nice talk. Can I ask about the CI loop? I imagine you have to have your hardware in the loop there. Once you've tested and you've done the factory acceptance, or could you comment on what we should be doing in the future in terms of, can this be kind of for integration testing, or in the future if we wanted to rerun the tests? Just because, with GitLab, it'll run some, it'll spin something up and close it down if it's just regular software. But if you have your hardware in the loop, it's a bit more complicated. So I guess my question is, what are your takeaways for hardware in the loop going forward into future testing?
Yeah, well, I guess so. One aspect is that we can repeat the tests with any version of any component. So we can specify we want version 7 of the processor or version 8 of the firmware, and whatever. We can mix and match new versions. So if someone comes back and says, well, it's been worked on the version. We can also obviously then look in the future versions. But yes, the hardware is important. We can't simulate this stuff, it's too complicated. So we use the hardware. We have a test facility in Marsfield. It has our FPGAs and network switches and everything all together. Or to, we try to set it up so that we can share continuous integration tests that get run ideally whenever something changes, as well as interactive debugging, so that Kubernetes systems share the resources. Yeah, does that answer your question?
I guess so, yeah. I'll check it later as well.
Yeah, sure.
Thanks.
Patrick, I'm curious about I guess forward compatibility of the design. How wedded are you to a particular hardware kind of platform or concept at the moment versus being able to adapt any changes to make more efficient, stuff like that?
Yeah, sure. So one thing I also forgot to mention is that we are actually, as part of the AI2 delivery, we're changing the hardware platform. We use commercial off-the-shelf FPGA cards. And certain components become hard to procure, so we come obsolete when you buy the next version. I'm not a firmware engineer, so I don't know how difficult that conversion was exactly, but it's just the same vendor. There's a path forward, but there is work involved, yes, in porting to the new architecture, but you also get benefits. It's twice as powerful. So the AD cards being less network switches, less services, power consumption, etc. Yes, so is able to be ported to future ones.
And if we do not have more questions, then shall we move to the next talk? And from move on, let's know some for we okay. Good afternoon, everyone. It's my pleasure to give our recent work for the H1 Galaxy funding by the FAM graphical scan service. I'm Yu Gang Wang from the National Astronomy Observatory. We know the first telescope is the largest single dish in the world. The spherical reflector has a radius around 500 meters. During the observation, the immediate aperture will become to 300 meters, and the scale coverage is large. The scale can cover around the zenith, around the minus 40 and or plus 40 degrees. So the full square will be covered more than 20,000 and 24,000 square degrees. For the first telescope, there are two receivers. One of the L-band receivers, this is the mild beam receiver. There are 19 beams. Another one is wideband receivers. So at present, the first telescope work in the L-band. That means we have the 5 beam receivers. So when we are interested in the H1 galaxies, we know that the neutral hydrogen is the most abundant element in the universe. From the H1 galaxies, we can use it as a good precursor to start the cosmology, because at the H1 galaxies, we can take it as the galaxy, just the optical galaxy.
we can use them to detect the power suppression. Then we can construct the cosmology. Another important reason is if we see this picture, this is a galaxy from the optical observation. This is from the radio H1 observation. We can see there are different scenarios, so which will give us a different physics. As we know, in our standard lambda CDM model, there are two problems. One is the first one is the missing satellite problem. That means we can find many satellites in the simulations, but we only found only 1%, 10% of the satellites in observations. The second one is the too few problems. That means in the simulation we have found many large satellites, but in the observation we didn't find. The third one is the simultaneous distribution problems. That means for the distribution of the Milky Way and the M31, the satellite distribution in the 30 planes. So, of course, these problems are found by the optical surveys. In the radio observation, it is possible to detect such kind of galaxy. We might call it the dark galaxies. So for this galaxy, we have the neutral hydrogen, but we don't have the star. So we cannot find in the optical galaxy. So if we can find this kind of dark galaxy, then we can help to solve this kind of three problems. Another thing is that we know we want to do because the mapping can increase the signal to noise ratio of the signals. If we do the if we detect the H1 galaxy, we can help to check the calibration process in mapping. We have the drift scan survey. The name of this survey is further. This is a Chinese name. Names. The English names means the problem, the origin of the universe. This is used for drift scan survey around the zenith or faster telescope. The reason we use the drift scan is that if we use this kind of the service, the telescope is stable. And around the zenith, that means the gain of the telescope will be maximum. So we have developed the full code reduction pipelines from the origin data to the last pipelines. We have published this paper, and we have put our pipelines FPIPE on the lines. So we need a different team to do H1 galaxy searchings. This here I showed the example. This is the SKA data challenge challenging tools. So for the SKA data challenging tools, the main aim is to search the H1 galaxies. We know from the whole world, more than 26 groups have joined this challenge. But we know the scores are different. That means even we use the similar method from the different conductor, different results. We know the advantage of fast lens is the ability to detect very weak signals, but the judgment of the weak signals requires extreme cautions. That's why the reason we need two different teams to do this kind of things, that we can cross-check the results. Actually, at the early time around the 2000, which we have begun to start the possibility to use the function to detect the very faint satellites. So this is the forecast start. We found if we use the faster telescope, we can detect 36 actual satellites galaxy with this mass ranges. That means if we have the different integrations more than 30 minutes in wide region, we can detect the H1 galaxies below 10 to minus 5 solar mass. So we can use two kind of methods to do H1 galaxy search. The first one is much bigger method. That means we can assume the galaxy, the special galaxy following a Gaussian mapping Gaussian distributions. We can move the filter. If we found this kind of the peak, we can select it as a candidate. The second one is the Sophia. This is a source-funding operation for data cube. That's here we use smooth collapse. That means we use smooth both in the special and the special simply. We can find if the peak is above the threshold values, then we determine it's H1 candidates. So this is the main result. So at present we finished the 60 degrees forming. So we developed our candidates for the different code members. For the code ones, that means this galaxy also found in the alpha surface. So we have found this kind of galaxy numbers. For the polar cells, that means this galaxy has founded on by the alpha telescope, but we didn't find that fast. The reason is that there is a strong alpha during the early observation fast. This strong alpha from the compressor. So we can, there are many alphas. That means this galaxy also can be detected by the fast telescope if there is no such kind of alpha. We also consider the 10 galaxies that's named the Kudu-2. That means this galaxy have also the SDS special informations. We also found some galaxies. This is only have the photometric galaxies. We also found some galaxies. There is no optical counters. There are around 8 galaxies. We have checked this galaxy. This galaxy now possibly is a dark galaxy candidates. So this is very important. We also combine the two methods. It seems that the two methods have good consistent expressions for some weak galaxies. So we also give more detailed comparison our result with the alpha surface. So this is the detect flux comparison is we can see that our result have good consistency with the alpha result. This is the difference. The history shows the difference for the flux. It shows that that is around 16% for this for our result with the alpha further. This result is acceptable. We know in the early times, even for the alpha sub, the single dish result is different from the large beam result. We can also estimate the soft noise for the both of the fast and the alpha survey. So for our surveys, for each day, for the first day we use fast the mentioned beams. For the second days, half of the beam covers the same region as the previous days. So that means in our data scans, each region also scanned by 2 times. This is similar to the alpha surveys. This is the estimation for the some noise ratio from the fast between the fast and the alpha surveys. We can see that since the two telescopes have similar system temperature, the only difference is the absolute temperatures. So we from this equation we can see it clears the fast telescope is more sensitive to the alpha telescopes. So this is derived from the H1 mass functions. So we can see the weakening our detect the H1 mass function is larger than the alpha. But in the middle regions, we can see the alpha result is larger than our results. The reason is that in the early observation of us, there are strong RFI. We have shown that. So there are many galaxies we labeled as put feather. We can also see in this region, our galaxies, in the heaviest area, we get the many high mass redshift high mass galaxies. The alpha. The reason is that we found this galaxy has a redshift less than 0.06. We know the highest redshift according to but the alpha is that it's around 0.06. But in our observations, there are some galaxies the redshift can be larger than 0.06. We have estimated the sensitivity. It seems that the alpha can also detect this galaxy, but they didn't detect such kind of. The major reason is that in the alpha observation, in the high redshift, there are strong alpha. So that's also the alpha reasons. So for our observation, there's also a large challenge is from alpha. This is already data, so we can see clearly there's a large galaxies. We can see is significant spectrum, electron spectrum. But if we get this galaxy from our math data, so we cannot find it. The reason is that as a printer, all of the alpha label master depend on the threshold values. If we use small threshold values, then most of alpha will keep will be kept in the data. But if we use a large threshold value, then even this kind of galaxies can be taken as alpha, and so this is very difficult to select a reasonable threshold values. We also found there is other things. Sometimes there are some individual people have some problem. For example, this is the beam 15. We can see this is around there are two times there are strong signals. We have checked this. There are strong alpha, and the signal that these alpha signals, the spectrum is similar to the H1 galaxy. So at the early time, we mistake this kind of things as the H1 galaxies. If we have the lots of data, it's very difficult to check this kind of things. Except for the H1 galaxy, we also do the H1 observation session because as the high redshift is very difficult to detect the H1 galaxies. So we also found the H1 observations. So we have get the last blender survey result for the H1 observation. We have found 56 the H1 observers. In the more in the 8,000 square degrees regions. So for the future work, we will improve the alpha planning. We will detect the H1 galaxy, the new mapping regions, because our survey is still ongoing. We can get more observation tests, and also we wanted to do the volume observation for the planets for the dark galaxy. This is very important for us to understand the lambda city and models. I stop here. Thanks.
Jen?
Just quickly, what is the H1 column density sensitivity? What is the column density sensitivity?
This is for one filter scan is around 10 to 19. around the 2019, yeah.
I have a quick question. What's the current progress of searching for these small H1 galaxies using fast? And what's the progress on how many galaxies discovered?
Oh, yeah, we have, at first time we have, estimate this kind of thing by use simulation is similar to 2 times, the H1 galaxy we can detect stuff, in this region as a alpha. The principal number is around, 1 square degree, maybe we can detect, we can detect 3 or 4 H1 galaxies. Yeah.
More question? No, then we'll go to the next speaker. The next talk is about Australia SKA Regional Center. The director of the Australia. Okay.
Hello, everyone. Today I'm going to give an update on the SRC. So thanks to Lewis, you already have a bit of an introduction on what SRCs are. Sorry. Okay. So SRCs are regionally led hubs that provide the resources that are needed to process and distribute and utilize the data coming from the telescopes. There's around, probably once telescopes are functional, there'll be around 700 petabytes per year of data that will be released to the users, and hopefully in a science-ready format. And so SRCs will be the only user-active interface to interact with the data and to do science with that data. All those SRCs will work together to form the SRC net or SRC network. And so this is a federated network of SRCs, and they're federated because you can log in, doesn't matter where you are, but you'll have the same access to all the tools and all the data as per your PI specifications, and it doesn't matter where you are. And so that's why it's all federated and networked and linked together. These will be spread out across the host countries or across the partner countries of SKA. And they'll also host the data, the science data archive. And so for PI science, obviously the PIs would have first access, but eventually that data would then become open access, and it will sit in the science data archive. And the goal of this is to enable scientists to focus on the science and not worry about the underlying compute and all tools and all stuff. So with the teams, we're trying to build up all those different software packages and tools and pipelines to hopefully help users work with this large amount of data. Here is the blueprint of the SRC net. So you can see, as I mentioned, those science enabling tools. So everything from Jupyter notebooks to any other algorithms and other tools that people are used to using, especially the visualization tools, for example. And there's also other tools for data discovery and data management and all that. So all this fits into the end-to-end science pipeline that science operations things for SKA. So you can see the first few squares, that's the observatory's responsibility. For that one to move over and get that science-ready data products, then it goes into the SRC nets, and where advanced data products are created by the users and then shared and also put into the archive. So the SRC is Australia's portion of this federated network, and so this is the mission statement for the Australian SKA Regional Center, and so it's to enable that scientific output, again, helping those scientists really work with the large amounts of SKA data, and leading in that effort to make sure internationally everyone can work with data. Because of our proximity to SKA low, there will be a bit of focus on that, but we would have access to both low and mid data. And you can see here on the bottom, there's our funders and partnership. And so we're funded by the Australian government, a $63 million grant over 10 years. And then we have 4 partner institutions, CSIRO, Curtin, Fuzzy, and UWA, which have in-kind contributions and also support the partnership. Here are the sound faces of the auxiliary personnel. So the top row is the management team, and then we have a bunch of developers, scientists, admin personnel, and operations staff. There's one bubble for a couple of people who will be starting soon, and if you want to join this team, stay tuned because one of my slides might try to recruit you coming up. But yes, lots of smiling faces and a nice team to work with. So here is the 10-year plan. We're already quite into it. Basically, for AUSRC, it was broken into 2 phases. The first phase was to build up functionality, mostly facilitated by the precursors, and particularly those in Australia. So we're fortunate enough to have both ASCAP and MWA here. And so working with those precursors, working with the scientists especially, and trying to develop pipelines and workflows to enable their science in a much easier way, especially as their data products are getting bigger. And as we're doing that, we're also helping to establish the global network, the SRCnet, and hoping to build up that. In phase 2, it's mostly just building up an operational readiness level and increasing our storage and compute and all those capabilities while continuing to build up that SRCnet. So here are is a list of some of the projects that we have worked on. This was work done during the past few years, and we supported, as I mentioned, the Australian precursors, so mostly ASCAP and MWA, and some key projects on what we did. And you can see that it's mostly working with different post-processing workflows and pipelines to ensure that scientists can do their science and not worry about trying to extract all the individual data products and work with and fight with the computing. And so all these workflows are basically automated and working, and those were now passed on to the operational side. And so those run, if chosen by the scientists, in the AUSRC operational side of things. So we host a couple of these databases still, and we still run these workflows, even though they're completed. It's mostly completed because of development work. So stitching together those pipelines and workflows, that's all been completed. Recently, we had a call for EOIs and then proposals to get more of these science enablement projects. So now we call them ASIPs. And we had, asked the Australian community, mostly working with the precursors, what they needed. And so about 20 projects submitted EOIs. 14 of them were then invited to submit proposals from those EOIs after working with our team to understand their actual needs from both the development and the science support side. And from there, the 14 proposals were then presented to an external TAP who evaluated them for the aforementioned details of developing pipelines and workflows, but also the pathway to the SKA, because we're still building towards supporting the SKA, building that functionality, as I mentioned in phase 1, what we're doing. And so the pathway that led to the SKA is the best. And so these were the 8 that were chosen. We're calling it best effort support because we are still building up our team and our compute resources. And we're supporting them for about 12 months, so that might slip to about 16, but we'll see how that goes, depending on timelines and how far we get with each project. You can see it's a mix between ASCAP and MWA, and then there's also a Meerkat project in there as well. Here is just some of the examples of the work that some of the developers are doing at AUSRC. So this one is a scalability test in the SRC net. Thanks to the talk before me, we kind of heard what Sophia is. Sophia is a source finding software package. Sophia 2 is a parallelized version of that. And so it's written in C or C++, I'm not quite sure, but it's more parallelized. And so you can break up the cubes so we have a data cube there, and you can break it up into chunks and then do the source finding on individual chunks. And then you can spread out on your compute. So it becomes an embarrassingly parallel project. And here we were testing, or the developer was testing, Austin in this case. He was able to load in a 2.5 terabyte cube. Thank you to GasCap OH for providing that, as we're supporting that. And it went into the pipeline there, and it's a next flow driven pipeline where it then chunks the big cube up into subcubes and then runs the source finder. Right now it's just running Sophia 2 because that was the easy one that was there, but GasCap OH is trying to do a couple other source finders as well, but it spits out all the details and then it puts them back into a standard, a single text file for the user to then interact with and do their science. And so here is the results of that scalability test. And so even though it was a very similarly parallel program, because it's chunking and then running the same source finding thing on small individual cubes, it did actually take more CPU hours as we went further up. And so those first two section line cubes were Willoughby cubes, and that top one is the gas FOH. Again, these are spectral line surveys on ASCAP. You can see that it took a bit more CPU hours than expected. Well, actually, that was expected, and most of the limitations that we found were due to the file access system or the file access contention, and then the general system setup. And so, as we're building the SRC net, we're taking these things in note and trying to make sure the environment and the type of file system that we're actually choosing works for whatever pipelines we're running. So I might note that this one, I think these tests were run on the Photonic system, and so there's a bit of file access difference than what the SRC net is running, but these tests will also be performed on SRC net. Rini was setting up the Ruscio thing. So it was mentioned earlier today that Ruscio is the data managing and storing tool that's being used to also move data around the SRC nets. And so we've deployed one of the Ruscio storage elements currently on our Oracle cloud server. And so we are using Oracle VMs at the moment to see if that works in commercial ones. So we'll test it on Amazon next, but the first one was just to get it on Oracle. And right now it is working. And so you can set up this whole Ruscio backend on a commercial cloud system. And we passed all the tests as of last week for SRCnet. And so it could be possible to actually start running this system. We won't because it is commercial cloud and cost a bit, but it was a proof of concept to try to do it. And this one we can now migrate over once we get our own compute. And so here is that same setup, just schematically, so you can see that there is the central global services, so the Ruscio server, and then it connects to all the other SRCs as you have those Ruscio service elements, and they just move the data around, and that's the thing that they've been testing, moving all those files around the network. Speaking about compute, so I did mention we were using cloud compute, and that's because we're in the process of procuring our own systems. And so the initial procurement is happening right now. We're trying to get systems set up at the Quasi Supercomputing Research Center, that being one of our partners. And we're hoping to have a compute system that has up to 1 petaflop of compute with an OpenStack cloud platform on top of that. And from there, we can also put on those commercial clouds, so Oracle as well as Amazon. So we're working with those two commercial companies, and we can transfer things over. So as we're setting up our cloud systems, we can just move them right over once we have our hardware delivered and installed. Storage, we just got the contract last week for this one. So we have 20 petabytes of storage at Quasi now, so 10 petabytes of warm storage. So those who use Quasi, they might know it's the Acacia system. And so we have that. And then there's also 10 petabytes on Banksia system. With Banksia, there is a redundant memory thing or storage, redundant storage. And so it's about 5 petabytes of usable storage because you have to have a copy of it. And that system we chose because the precursors are already working with it. We know it works well. And in the meantime, while we're working to integrate our system and to build up to integrate it into the SRC net, any extra storage or even compute, we can then put back to supporting those precursor projects that we're supporting locally. And so that those ASCAP, MWA, and possibly MERCAP projects. So that was our future plans, so that was our initial procurement plan, and now this is a bit of a tentative plan that we're looking at where we expand to. So once we get our initial system set up at Quasi, we are looking at then expanding across to the east over here, possibly having either similar compute at Macquarie and Swinburne or something totally different depending on what we need it to do. So just like how the SRC net is individual nodes all over the world, SRC will be individual computing centers all over Australia, hopefully, as we move forward. And that will help a bit with the load of where the data is. And also, if one system goes down or something happens, we have backups. We will also have backups in the commercial cloud, but this just has a couple of local backups as well. And And then we can make sure our system is running. So we are in talks currently with Macquarie and Swinburne. These are less mature than the actual procurement that we're doing with Quasi, but this is the broad. And to make all this stuff work, SRC is recruiting. So here's the org chart. So the ones in red are the positions that we're currently about to recruit for. And so you can see there's a bunch of developers, support scientists, and a DevOps engineer as well. We would like these personnel to start sooner than later, targeted recruitment by the end of the calendar year. And so for my last slide, I'll put up the job availability. So you can use that QR code if you have any friends, you know anyone who might want a job with the SRC. Remember all those smiling faces are great to work with. So the support scientist one that closes this weekend, which is usually fine because I noticed scientists do leave it to the last minute to apply for jobs. So you still have plenty of time. And then we have up to two senior developers that we're also recruiting, and that closes next week. Soon to be advertised would be another 3 senior developers and a cloud DevOps engineer. Note the locations for those ones. So those will be on the East Coast, at least some of them, hopefully, and that will help our expansion as we're moving to having systems at possibly Macquarie and Swinburne. Thank you.
People are very effective. Present comments. Present. Can I have one point that when you're talking about that you comment that you have the compute and the storage, and the compute is on the OpenStack cloud. Is that physically in the policy or outside?
We're buying that right now, and so we're trying to get that. So as of like last week, I think we got one quote from one provider, and the other one should be in today or tomorrow. And then once we get those, then we can go ahead. Procurement will probably take anywhere from 2 to 3 months is what we're getting told from the vendors, and then we'll have that at Quasi. So that will be harvest.
So we just pay for on
Yes, it'll be on-premises hardware. And then from there, we can then install the cloud stuff on top of that as
well. More question or comment? Yeah.
Right. Are you working with the other SRCs for all this development, or does each SRC work individually?
So for the SRC Net initiatives, we're working together. And so for that ratio stuff, for example, we had people from China SRC come in and help us out and set that up, especially this past week, a couple of the bug fixes. For the science cases, at the moment, we're working individually for that because SRCnet is not at the point where they're enabling science. They're still trying to build up that federated system. And so that's why it's more of the scalability tests and the building of that network. And so that we're working together. As we move further, we do want to work with SRCs directly as well to enable that science. That's why we started that one Meerkat project to try to get the South African SRC working on it as well. And so we're building up to that.
More question? We have much time.
With the source finder having trouble on the really large cubes, what's the kind of, I mean, that's a big problem, right? So, and then cubes are going to get bigger. So what's the kind of plan on how to solve that particular problem?
Yeah, and so, and that's what they're trying to figure out right now, because everyone's like, oh, well, this scales, and it's like, actually it doesn't, right? We're trying to find things that do scale. And so part of that was that file system thing that Quasi seems to have. And so they're testing something else in SRCnet to try to solve that, but either rewriting the algorithms or trying something else. You can't just keep throwing compute at it is what we're finding, unless it's a certain type of compute. So maybe it has to be more bespoke for certain pipelines to run properly. And so that's what they're testing right now. It was still nice that I could run a 2.5 terabyte cube. That was,
yeah, that's great.
We've come quite far.
Okay, and you may have no more questions. Let's thanks to the speakers in these two sessions again.
I think Tara's part is done now, so we will be back at 4 o'clock. So you get a bit of an afternoon tea break for the last part of this session. We'll have two speakers. So you just heard about the Australian Regional Centre. Tara will be on the other side of the microphone talking about the SKA, the China's Regional Centre. And then we'll also have a talk from Ruta Kale about data processing for SKA. So two very important, interesting talks to come. Thanks. See you at 4.
Thank you.